Good morning, DJ, and thank you very much for the introduction, John, for your patience with loading the slides. I am presenting on behalf of my research associate. He wasn't able to make it. He was supposed to be the presenter. He's now with HNTB. This work is based on his doctoral dissertation, which it was done, I believe, in 2017. And there's one paper in ACI that he already published, but this work, we're looking at it from a different angle. So the idea here is when we refer to hybrid tendon, is that sometimes, and this came up in a discussion with our Department of Transportation, where they have placed a moratorium in using unbonded steel tendons because of the issues of corrosion. As a final product, they won't allow it, but during construction, it is allowed. One of the issues they had in Victory Bridge is that the grout was, and in grouting on the unbonded tendon was having a lot of chloride at that time. So there was a concern. And we suggested that to replace the unbonded tendon steel with an FRP tendon, and they liked the idea and they supported us to look at this combination of steel bonded, pre-tensioned, and FRP unbonded. So you end up with a section having bonded and unbonded. And therefore, we called it hybrid in the sense that there are two ways to calculate the moment capacity. AASHTO have addressed that problem for segmental, but it was really a Band-Aid. It wasn't a real fix, and we'll talk about that in a minute. But ACI doesn't really address situation where the beam has both bonded and unbonded tendon at the same time. So what I will talk about is the testing that we performed to be able to look into this feasibility of using this combination. And we also tried to get a baseline for the comparison, which is bonded steel beams, pre-tensioned, unbonded steel beams, a combination of bonded, unbonded, made both out of steel, and also a combination of bonded steel and unbonded FRP, or vice versa, bonded FRP and unbonded steel. So the idea is to marry the two together so that we can get, the main thing here was focusing on the ductility performance, the cracking behavior, as you know, because we know as far as the capacity and the safety, they're very comparable, even better. However, the concern from our engineers at the state was that, do I get the same cracking behavior? Do I get the same ductility? Which code am I going to be governing this? And many of the designers, the minute you start talking about design, they want to stick to the playbook, which is the code, and they're not willing to really go outside what the code says. So for that, we tested so far about 40 beams, but the 18 beams were made with Aslan type of tendon. We have also follow-up study with the Tokyo. But today, this presentation is only relating to the Aslan type of straight tendon. We'll talk about a little bit about what ACI 318 says and what ACI 440 approach was. And we added the finite element just to do more simulations and do more parametric study, which is not really included in this. So as I mentioned, this is the background. Especially in segmental bridges, this is really used heavily, the bonded, unbonded, but also a lot of parking structure. A lot of, you would have maybe reinforced concrete, and then you apply external pre-stressing to, beef up the capacity. Sometimes there might be a pre-stress girders where you come back and you do external. So this bonded, unbonded, the unbonded could be internally unbonded or externally unbonded, meaning an external tendon. And from our results, initial results we found out that the new hybrid system is really comparable to steel. And we should really push that, and that's what we're trying to do. So the background about the corrosion, there has been a recent paper which has really covered exactly what happens. We have also, I'm part of the team who's doing the NCHRP 12-123, which is the load rating of segmental bridges. And we collected data. There's about 400 segmental bridges in the United States. We collected data on the performance. And to our surprise, that they were doing very well. However, some of them even, if you see in the next slide, some of them that are 9 years old and they're starting to corrode. They are the unbonded side of it. So there's a mechanism there, and unfortunately, if you don't do a visual inspection, does not really pick it up. You have to do a very detailed inspection, perhaps sometimes do some probes, remove some of the concrete to look at the tendon. So that's really, very detailed, and so the idea is, why don't we replace steel and put FRP in conditions where durability is of concern? I think that seems to be fitting very well. So the concern was, if I do that combination, what would happen to the overall performance? So the objective was, look at the testing in the lab, find out. So we ended up testing 18 beams at the time. And we also performed some analytical study based on, we have some modeling, which is not part of the study, but the same model that was used, modeled in Abaqus, we also derived the equations analytically to have a closed form solution. So this is just to give you an idea about the testing setup. So we had a simply supported beam, about 3 meters clear span, and 2-point loading, flexural. We tried to measure deflection at different points, and also to be able to get the curvature over the length. So the notation is a little bit, I need to spend a little bit of time explaining this. So when H means it's a hybrid, so it's a bonded, unbonded. X here, if it's F, it means it's fiber, CFRP, and if it's S, it means it's steel. Okay, so F. So if I say HF, it would be hybrid beam with the tendon in the unbonded being FRP. And also the prestressing, if it's A, stands for if it's either unbonded, or B stands for bonded. And the last one here would be the different diameters. We were constrained by the different diameters of the tendons that we could use for this small scale testing. So sometimes we use 3/8 in steel, but the equivalent in the CFRP is not exactly 3/8. So we try to either base it on the area, or base it on the moment capacity, or even base it on the effective pre-stressing, so the force would be approximately the same. This is the table of all the 18 beams. I'm not, this is too much to cover, but a lot of beams here just to show you the notation. So we have 2 types of beams, bonded steel, same dimensions, and this is the effective pre-stressing here. If it has unbonded tendon, if it has bonded here, if it's HS, it's steel, and the F is, and sometimes we place the unbonded on the bottom and the bonded on the top, which we usually like to have the bonded on the bottom because that's what we need to get the more capacity, but the difference is slightly small. Now with this combination here, when you have bonded, unbonded, we try to figure out what is the reinforcing index in that one. So if you look at the code, it's usually for fully pre-stressed or fully pre-stressed with non-pre-stressed reinforcement, so there's not much in this. So we ended up coming up with what Naaman has done, which is the effective reinforcing index to include all, so basically you're looking at the total concrete, tension force divided by the compression force. So basically that's an indication, and we try to add that so that we are consistent, or at least we know if that's a factor, we know between the beams how that is going to change. Just quickly, this is so we did the load deflection, and we tried to also, as I said earlier, to do the moment curvature, but this is based only on load deflection for now. And you could see that the unbonded steel, and the red here is the bonded steel, okay? And this is the unbonded steel. And they're very similar towards the ultimate, but a little bit the stiffness, and this is expected in unbonded, but at least they all give you everything like above 80 millimeter in terms of the deflection. So there's that, you can see that the ductility there is existent. However, if you look at, and some of the, like if you look here, for example, it's the bonded and unbonded, both are FRP. We're not getting more than 80 millimeter. okay, in this combination. When you bond the FRP, then the ductility is reduced. So the best scenario is to keep the FRP unbonded, and that can be a good mechanism to show that the behavior can be improved. But look at what happens when we do the unbonded, the steel, for example, here, if this is the unbonded and both bonded and unbonded FRP, and here you can see here, this is the steel bonded, but the FRP unbonded. So we are starting to get over this threshold in terms of ductility. So the system, in a way, you know, when you combine the two, it starts giving you a little bit more ductility. And these are some of the results. I know there's a lot of information here. I do apologize, this is too crowded. But I didn't have a chance to, he you know, did this work and kept it on the same last minute. So we tried to look at, okay, so now the concern was ductility. We like to look at the traditional definitions of ductility. You know, this is you have to get the deflection at ultimate divided by the deflection at the yielding. The thing is that when you do FRP bonded, there's no distinct yield. So it's very difficult to get this value. And this is another definition by Zhu here, where, you know, there are many definitions in the literature on the ductility. You know, sometimes people, instead of using deflection, they use curvature at ultimate and curvature at yielding. But as a designer, you don't have a priori, you don't have this number. You know, so you can't get the load deflection ahead of time, so you would know if this is ductile or not. Then we tried to look at what does ACI 440 say about that. And instead of, it's not clear, you know, this is the 440R was a great document, I think, for the time. And needs, I think, in my opinion, it has good stuff in there, but it needs a little bit updated as far as this bonded, unbonded. That was not being considered. But one of the things, and I think it was mainly focusing on bonded FRP. And if you read that carefully, what they're saying in there is that they use balanced condition. That means when the concrete is crushing, the FRP is going to rupture. And in unbonded tendon, that's a no-no. We don't want to do that. Maybe limited to 0.9 FPU, but this is not a very good approach for unbonded. And, you know, you might utilize the FRP capacity, but not to that point. So that approach, I don't think we can apply it the way it is right now in 440. It needs to be changed. It cannot be applied to this situation. If you look at comparison with 318, what do they do in 318? Well, if 318 changed, you know, when Mast did his paper in 1995, they shifted to, instead of going to row balanced and all of that, he said, why don't I look at the strain and the tension reinforcement? If I have non-prestress reinforcement, the strain has to stay about 0.003 plus the yield, where the yield is about 0.002, so that's about 0.005. And if you have fully pre-stressed, you limit it at the tension reinforcement in the bottom, you limit it to 0.005. So that's a very quick way and very efficient way. So you don't care if it's bonded, unbonded, reinforced concrete, partially pre-stressed, it doesn't matter. You could just apply. However, that doesn't tell you the whole story. It doesn't tell you about, these are a limit, either yes or no. Okay, I could be very close to this limit, and I might not have the load deflection, I might not have the moment curvature that I need. Therefore, both approaches, I believe 318 is much more befitting and it's still applicable, but it needs to have a little bit more details about how do I deal, which beam is more ductile. It doesn't tell you that. So this is some of the result. We looked at the beams that we designed, and we looked at what type of failure we had. So some of them were tension controlled, but the majority were compression controlled. You know, the concrete failed before that. We also looked at how does the 318. If you look at the failure, according to 318, there's a slight differences between the interpretation between 440 and 318. The inconsistency in the type of prediction is really, we need to zoom in and work on that. I'm hoping with the 440i will address something like that.
You're leading that chapter. So.
We'll see. Well, we'll see. I can't do it alone. But okay, so we looked at what 440 is basically the approach there. And so 440 looks at, okay, fully cracked section. We use IE with the modification that Wasim just talked about a little bit. But it's still using the older beta D, right, which is still applicable. I think it gave reasonable results, right, Wasim? And the iCrack is fully cracked section, so you need to have the neutral axis, for a fully cracked section. The problem is when you have bonded and unbonded, how do you find the neutral axis? Okay, so either you have to do strain compatibility approach, meaning that you solve it incrementally, and you would find the strain in the bonded tendon using the compatibility of the strain. If you have non-precise reinforcement, you would have to do the same. So it's a very lengthy approach. But nonetheless, this is what's in 440 right now. And we also, for the unbonded, they ended up using, so this is the equation for bonded. Okay, from compatibility, you can see it. But this equation here, it uses the equation developed by Al-Khairi and Naaman in 1991. And it has the gamma factor, this omega factor, and this omega factor for this case is considered constant. What is this omega factor? This omega factor, they propose that a unbonded beam can be converted into a bonded beam by assuming the strain, the strain of bonded over unbonded is this omega factor. However, the strain, once it cracks in elastic range, that's beautiful, right? You could do that. And this is based on what Baker did in the 50s in England. But once there's a cracking, then the strain is going up and down. It's very difficult to have a function that can integrate that strain and for an unbonded tendon and then do it for a bonded tendon. So that approach, I think Ashto moved away from that. This was the equation that Ashto had up to about 2001. And then they moved away from it for this reason, because it was based on experimental data that had all steel tendons. There was no FRP tendons, so it's really limited when it comes to FRP. And I'm not sure at that time why it was used. And then you are able to find this equation here. So 440 for the time, I think it did the best it could. Ashto had a fix. So basically, for unbonded, they say, well, forget about, we'll use the effective stress all the time, which really underestimating the capacity from, for this one. And if you have bonded, unbonded, we'll take the average of both stresses, and the weighted average depending on how much bonded and how much unbonded reinforcement you have. So really, and if you look at, so we calculated the accuracy. This equation 440 does a great job in predicting the moment, the curvature, the moment and the deflection. You could see that, for example, at yielding, it had the average prediction was very good, and here the moment was very good. However, for the ductility, it wasn't very good. We did the modeling. I'm going to go a little bit quick here. We did the finite element modeling based on this model, assuming what we tried to decouple the unbonded tendon from the bonded tendon, so it becomes like a beam. This is the concrete element. It will have the bonded reinforcement and the bonded non-precise reinforcement, and the unbonded tendon is free to move since it's unbonded. And we did the modeling on that basis, and it did really very well, okay, compared to all the beams. So we were able to have a tool to basically go beyond what we did in the experimental. And if we look at the predictions in terms of the load, and we try to look at the model does really great job in getting the deflection and the moments and the ultimate load. But if you look at what happens with 440, again, as I said, the cracking moment is very good, the ultimate moment. But look at when we're trying to predict the curvature ductility, using both definition. It's really not that good for ductility. And that's probably one of the reasons that, 440 need to address that, Because that's always the key outside. People throw at you that, okay, what about ductility? What about cracking? What about fire? All of these things, we need to find ways of doing it. So I think using a FRP now as a unbonded in this hybrid system can improve ductility, can give you exact same cracking behavior, same crack spacing, crack width. It's even better that once the unbonded tendon does not fail, the cracks will close. Even when you unload it, the cracks will go back to really being very small. So the ICI prediction for ductility need to be revisited. That's the main conclusion, and we're hoping for 440i we will be able to do this work. I'd like to acknowledge we started this work when Recast. I was part of this with Dr. Kamal Khayat, Dr. Antonio Nani, and David Lang. This is in 2017. And then now we have part of this new center, so they gave part, and NJDOT. We have a bridge resource program. Thank you very much.
Thank you.